Hi, how you doing? Welcome to integration. If you've tuned in, then you're in for a treat, okay? If you made a mistake, do not stop the video, okay? Don't go somewhere else, just watch this, okay? You might just make your day, all right? This is integration. This is the first time we're going to introduce integration into AS or A-level maths, okay? Why do I like integration so much? Why do some mathematicians like integration so much? Well, for me personally, it represents a huge challenge, okay? Differentiation is where calculus begins, of course. Integration is the reverse of differentiation. So you might think, well, actually, yeah, sure, the challenge is just the same. Well, no. Okay, we're not really going to be able to show you why in this particular video. Okay, it's not really going to be until you're in year 13 doing A-level maths where you'll suddenly realise what I'm actually talking about. But you can almost differentiate anything. Okay, any function you give them can pretty much differentiate anything. You cannot do the same in integration. There's some things that are extremely difficult or impossible to integrate. Okay, it's not more challenging. Okay, because working backwards through a calculus result is not as easy or straightforward as you might think. Okay, so for me, I love integration because it presents a huge challenge in mathematics, and that's why we're studying maths, to be honest, isn't it? I'm not doing maths because it's an easy subject. Okay, well, some of you might be, but you're in for a shock because at some stage, you will find it gets difficult. But we're doing mathematics for a challenge. Okay, we don't just love it when we understand it and we can do it, but there's still integrals that people just cannot do or find extremely difficult. Okay, and you won't be able to see it now because you're in year 12. Okay, but when you're 13, you'll be able to see just what I'm talking about. Okay, but this is the beginnings of it. Anyway, so that out of the way, let's get on to integration. What's it all about? Well, I said it's the reverse process of differentiation. Okay, so let's just suppose you had a function and we differentiated that function, and suppose we got an answer of should we just say 3x squared? Yeah, okay, that'll do. What we need to do is find out what that original function was. Okay, so if dy dx is 3x squared, what is the possible function that y could have been? Okay, that's the reverse process of differentiation. Well, I'm hoping you're thinking that when you differentiate x cubed, you get 3x squared, don't you? Okay, so you might think, yeah, y is equal to x cubed. But that's not the only function it could have been. It could have been something different. Okay, it could have been, for example, this x cubed plus, I'm just going to put a number here, 5. Because if you differentiate that, okay, you get the same result. Okay, it could have been x cubed plus 51. Okay, it could have been x cubed subtract 1,000. Okay, it could have just been x cubed. Okay, but it's going to be x cubed plus some other value. Okay, that other value is very important. Okay, and we call that the constant of integration. Okay, plus c. Right. So the potential answers for dy dx equals 3x squared as a function of what y is in terms of x are y equals x cubed plus some value c, where c is any real number. Okay, and that is it. That's what integration is all about. Let's do another example. Okay, suppose you are given that dy dx is equal to 5x to the power of 9, say. Find out what function y could have been. Well, just think about it for a moment. Pause the video maybe. Do you have an answer? Okay. Right, well, you know certainly that it's going to look like that, isn't it? Okay, because when you differentiate, you decrease the power by 1, don't you? So you know it's got to start off x to the power of 10 because then that's how you get x to the power of 9, okay? But what's the coefficient got to be? Well, you know that the 5 has got to stay there, okay? But what are you going to multiply this by in order to get that? Well, it's this, okay? 5/10, x to the power of 10. Check it, okay? When you differentiate this, bring the power down, so 10 times 5/10 is just 5. Then x to the power of 9, you get this, okay? And of course, the possibility of having some constant in the end, plus c. You can simplify it, yes. You'd ideally write it as a half x to the power of 10 plus c, but that is what your function would actually be, okay? That's integration, okay? Now, I'm going to rewrite the same question, but a different way, okay? What I'm going to do is I'm going to rewrite it like this, so I'm going to say integrate. I'll use the same example, 5x to the power of 9 with respect to x. The WRT is shorthand in mathematics for with respect to. It's just quicker to write down, you see. Okay. And you know the answer is this, okay? 1/2 x to the power of 10 plus c. So that's another way of saying it, okay? So you could say, if dy dx is 5x to the power of 9, what potential function could y be? It is this, 1/2 x to the power of 10 plus c. Or you could say, integrate 5x to the power of 9 with respect to x, okay? And you get 1/2 x to the power of 10 plus c. And then a final way of writing down the same result, same question with answer, in symbolic form is this. We use this symbol here. That's the symbol for integration. It's an elongated S. Just think of a letter S and then just stretch it out, okay? The reasons for that will be shown later on, not today, okay? But in short, it stands for an infinite summation. I'm not going to say why, but there it is, okay? Look it up, okay? If you're one of my current students, the video is not available, okay? But if years down the line, you know, you're watching this, obviously I've made the video already, so you can always jump ahead if you wish, okay? So an alternative way of saying integrate this with respect to x is this. Integrate, that's the symbol for integrate, and then you put in the function you want to integrate here, 5x to the power of 9, and then with respect to x is that bit there, the dx, okay? So in symbolic form, this is what we're saying and what we're doing, okay? We want to integrate 5x to the power of 9 with respect to x, okay? And you can either write the answer here or here. If it's just a one-line answer, I sometimes just write it on one line, so 1/2 x to the power of 10 plus c. If there are several steps of working, I normally put the working underneath each other, okay? As I'm sure you're already aware, okay? So that is it, okay? So within just a few minutes, we've gone from an introduction to what integration is to this is a standard type of question that you need to be able to answer. Having done that, let's have a look at some other examples, okay? So I'm going to use the same language, of course, but I'm going to write it in symbolic form. So I'm going to ask you to have a go at this, okay? And that says integrate x to the power of 6 with respect to x, okay? Just mention the dx, okay? Of course, when we find dy dx, what that means is differentiate y with respect to x. So when you've got y equals, say, 2x cubed, this says differentiate y with respect to x. So the dx is always meaning with respect to x, okay? So that's why it's important to recognise that dx there is essentially the same as that dx there. Can you do it for me? Have you done it while I was just talking about that? Okay, well, I'm going to put the answer underneath actually, because that's generally my preferred way of doing it, okay? Have you got x to the power of 7? Okay, because when you differentiate it, of course, you're going to decrease the power by 1, aren't you? Okay, what's the coefficient going to be? Okay, think about it. The coefficient has got to be such that when you do 7 times this, you get 1, x to the power of 6. The coefficient's got to be 1/7, hasn't it? Okay, 1/7 x to the power of 7. So when you differentiate this, you do 7 times a 7th, which is 1, then x to the power of 6. Okay, did you put anything else on the end of your answer? Okay, very good. If you remember the plus c, get used to it if you didn't, okay, because you are potentially going to lose some marks if you don't put the plus c at the end of a particular question, okay. Let me just mention now, this is called a general solution. A general solution because we don't know the exact solution. The plus c, where c could vary, okay. A particular solution is when we can actually substitute the values in and work out what that actually is. Not this video, but later on, okay. You'll see that later on, okay. Can we think of a general rule now of integration? So that is, if you were to integrate x to the power of n with respect to x, okay, can you think about what the rule is generally? Okay, because it's a general rule that you're going to write down your notes and write down the answer here. Well, of course, being the reverse process of differentiation, you want to increase the power by 1. Yeah, so whatever the power is, you increase it by 1, so n plus 1. What's the coefficient going to be? You can use this example to try and help you. Okay. Can you see that the coefficient is going to be 1 over n plus 1? And let's put the plus c in as well. Okay. So in short, as a summary, what you're doing when you're integrating is you're increasing the power by 1 and you're dividing by that power. Okay, so increase the power by 1 and divide by that power. Okay, so that's an important rule of integration that you'll need to have in your notes. Okay. Suppose you've got a constant in front of it, so suppose you're after integrating this, k x to the power of n dx, okay, where k is generally other number, okay. I'll tell you what sort of numbers they generally are in a minute. Well, if I just look at this one here, if I just put, let's just put a generic number there, if I put 8 in front of that, how does that change the answer? It just changes it to an 8, doesn't it? Okay, because when you differentiate this, 7 times the 7th is 1, and then you've got the 8 there. So you can see that coefficient there effectively just remains, okay? So when you have k x to the power of n, that's just going to be k over n plus 1 x to the power of n plus 1 plus c, okay? Now I should specify that in these particular examples that k is just any number, well not 0, otherwise it's a mere formality, you just get integral of 0, which maybe we'll talk about in a minute, okay? But n cannot be any possible number, okay? N is generally any real number except it cannot be equal to -1. Just want to take a moment to think about why n is not equal to -1 there. So I'm hoping some of you are thinking, well, there's a difficulty there when you have 1 over 0, isn't there? Okay, 1 over 0 is generally undefined, okay? So what I'm saying is, this integral here, 1 over x dx, which of course is the same as x to the power of -1, is not an integral that you'll do in year 12 AS Maths, okay? Because this rule does not apply, okay? Actually, you get a rather interesting result. I'm not going to explain to you now, okay? But the result you get is this, really interesting, okay? You get natural log of x plus c. So it's just a habit. I put the modulus brackets around. You'll see why that is much later on, okay? I'm going to rub that off anyway because you don't really need to know that now, okay? But suffice it to say, you'll see it in year 13, okay? So these are your general rules you want to have written down, okay? Right, let's have a look at another question involving the use of this rule, okay? So what I'm going to do is I'm going to ask you to integrate a few terms this time. So let's just give an easy one. So x to the power of 4, that's pretty easy, isn't it? Okay, and then plus 5x, okay, subtract 7 dx. Now when you're integrating more than one term, traditionally put the brackets to show that you're integrating all of that with respect to x, okay? Do you know what you're going to do? Yeah, just like with differentiation, you're just going to go through it one term at a time, okay? So integrate that, then that, all with respect to x, okay? So this one here, do you know what it is? Great, it's 1/5 x to the power of 5. And then this one here, do you know what that one is? That's good, it's 5 over 2 x to the power of 2. And this one here, do you know what it is? Great, so that's subtract 7x, okay? And anything else that is to go on the end? Indeed, the plus c. Now my advice to you is when you've got an answer to these, differentiate to check your answer, okay? You'll find that in this unit of integration, you'll be practicing your differentiation skills as well, okay? So if you differentiate these, you can check your answer, okay? So differentiate this, 5 times a fifth is 1, x to the power of 4, there we go. Differentiate this, 2 times 5 over 2 is 5x to the power of 1, so there it is, 5x. And then differentiate -7x, you get -7, okay? It's a bit like when you factorise, you can always check your answer by expanding the brackets again, okay? You can do that with this as well. So one important result there, I suppose, is that when you integrate just a constant value, okay? Integrate the 7, you get 7x. You don't really need to write it as a general rule, okay? But let's just write it down anyway. If you are going to integrate just a constant value, say k dx, okay, then you're just going to get kx plus c, where that k is any constant value, again, not 0, okay. Yeah, that's pretty much what you need to know about integration, okay. Should we do another example? Yeah, let's do another example, okay, because I do love doing integration, as I've already pointed out, okay. I just can't resist doing more examples. But sometimes I want to do so many on the board before I set my class off working through the textbook, okay. I just want to do this all lesson, okay, but you know, I shouldn't really, I should let them work on themselves on the textbook, okay. So let's have a look at this one. So integral of, I'll give you a few terms, square root of x subtract 1 over x squared. Actually no, let's make that more interesting. Let's make that 2 over x squared and plus 1, no. It's always nice when you've got coefficients there, okay, so 3 over square root of x, okay, dx, maybe just pause the video and have a go at that and see how you get on. Okay. I'm going to rub this off because I'm going to need to make space for some working with this. Okay, and I'll tell you what, I'll rub this off as well. Okay, there. Usually I clean the board, especially for today, especially for the integration. I clean the board. It's in such a good mood, you see, about doing integration. The sun is shining today. Everything's going right today. Everything's going right. You know, it's good. What are you going to do? Okay, well, same with differentiation. Put it in index form first. Okay, so rewrite the integral, but everything in index form first. So this will be x to the power of 1/2. And then put this in index form. That will subtract 2x to the power of -2. And then put this in index form. That would be 3x to the power of -1/2. Okay, dx. I'm assuming you're happy with that. You have to be happy with that. Okay. You see, well, you should have seen in the differentiation chapter why your rules of indices are so important, but you can see again, okay, you need to know instantly that is that. You haven't got time in the exam to start thinking, oh, how do you do that again? I'm not too sure. I can't. You do not have time for that in the exam. You've got to just bang, know it straight away, and just write down what the answer is. I can't believe I just said bang there. There you go. Right, integrate this then. My advice to you with these sorts of questions, but it's not as straightforward, okay, is to concentrate on what the power is first. Okay, remember the rule: you increase the power by 1 and then divide by that power. I've said it that way for a reason, okay, because the power is actually important. So this term, increase the power by 1, what do you get? You get 3/2, yeah, and then you divide by that power. You are going to be dealing with fractions a lot, okay, you're dealing with fractions a lot. So top-heavy fractions, please. When you're dividing by 3/2, that's the same as multiplying by 2/3. Okay, so that's important. You recognise the quick way of working out what the coefficient is going to be. I'll say it again. When you're dividing by the power 3/2, it's the same as multiplying by 2/3. Okay. Remember, as a check, differentiate it. Check you got the right answer. 3/2 times 2/3. Yes, that's right. X to the power of 1/2. That's it. Okay. Right, this one here. Okay, I'm not going to put in the symbol, okay, whether it's positive or negative, okay. I'm just going to focus on the power, because sometimes it changes, sometimes it becomes positive, sometimes it remains negative. I don't just fill something in and have to change it, is what I'm saying, okay. So increase the power by 1, be careful of these. When you do -2 plus 1, it's going to be -1, isn't it? Okay. And then you divide by -1, can you see? -2 divided by -1 is going to be +2, okay. That's it. Check by differentiating. Okay, so -1 times 2, the -2, decrease the power by 1, you get that. Okay, on with the next one. Again, we'll decide whether it's positive or negative at the end. So x to the power of, what's that going to be? -1/2 plus 1 is 1/2. Okay, and then divide by that power, divide by 1/2, same as multiplying by 2. Okay, +3 times 2 is going to be +6. Okay, check by differentiating. So 1/2 times 6, 3, decrease by 1, -1/2, great. Just do not forget the plus c. It'd be such a shame because, you know, it's a bit of an effort really, wasn't it, if we're doing this for the first time? A bit of an effort to integrate all of that. It's a real big shame if you lose the final mark just by forgetting the plus c. Okay. I know some students in the past, at the beginning of an exam paper, they wrote at the front of the paper, plus c, as a reminder for every integral question they do in the exam, they put the plus c in because they just didn't want to lose the mark. Okay, maybe that's a tip for you. Yeah. Anyway, I hope that you found that useful. I'm going to give you one more example because I just really love doing integration questions. It's just like fantastic. Okay, it really is fantastic. Okay, and the more of these you do, you know, the better you're going to be, of course. Okay. Maybe you're happy with it now, maybe you're thinking, yeah, I've got the hang of this, but just please do watch because there's only another few more minutes. Okay, so let's have go to another question. So let's do integral of, what can we write? So 2 plus 3x all over x to the power of 4 dx. Okay, I've just made it a little bit different, so I'm doing another style question. Okay. As with differentiation, you want to simplify that first, okay? I'm hoping you pause the video to have a go at it. all right? And you've unpaused it now to see what the answer is. So you want to simplify this, get it into two different terms, okay? So you've got 2 over x to the power of 4, okay? So that's going to be 2x to the power of -4, let's put a bracket in there. And then you have plus 3x over x to the power of 4, so that's going to be x to the power of -3, yeah? And then that's it. So that's the first thing that you want to do, okay? So remember 2 over x to the power of 4, which is the same as that, 2x to the power of -4, then 3x over x to the 4, which is the same as 3 over x cubed, which is 3x to the -3, okay? And then you're ready to go, you're ready to integrate, okay? So integrate this one, so what's the power going to be? It's going to be -3, and then divide by -3, so that's going to be -2/3, okay? Check by differentiating. -3 times -2/3 is going to be +2, great. Decrease the power by 1, -4, excellent, okay. This one, so increase the power by 1, you got -2, and then divide by -2, so you have subtract 3 over 2. Check by differentiating. -2 times -3 over 2 is going to be +3, excellent. And then decrease the power by 1, you got -3, that's good. And let's not forget again the plus c. Okay, and that is it. Well, I'm sure that's several examples that will allow you to get on with any exercise that you need to, okay? My advice to you is just practice as many of these as possible, okay? As I said already, integration does get a lot more challenging, not just a little bit more challenging, a lot more challenging, okay, in year 13. And so you really need to know it inside out in year 12, okay? I'd say differentiation and integration, you need to be really, really good with them, okay? You need to get 100% of the questions from those, because then it'll, believe me, it'll make a big difference to you when it comes to year 13, because calculus gets just a lot harder, okay? Well, I hope you enjoyed that, okay? There's another video coming up on some other applications of integration, okay? But I'm hoping that you enjoyed this one. I'll see you soon. Bye-bye.